This skydiver is moving down at a steady speed, even though the resultant force is zero. Shouldn't the balanced forces make them stop? Make a prediction. Drag opposes motion relative to a fluid. Air resistance is drag. Friction opposes sliding between solids, while lift is perpendicular to a relative fluid flow. In this fall, only weight and drag matter. Take downwards as positive. At the start of the fall, downward speed and drag are zero. Weight is then almost the full resultant force, so acceleration is approximately g downwards. But as the skydiver speeds up, air resistance increases. Weight stays essentially constant, so the difference between weight and drag gets smaller. The resultant force and the acceleration both decrease in their magnitude. The skydiver is not slowing down, their speed is still rising, just more slowly. Eventually though, drag equals weight. The resultant is zero, so acceleration is zero. The skydiver is already moving, so Newton's first law says they continue downwards at a constant velocity. The magnitude of that velocity is the terminal speed. Balanced forces do not mean no forces or no motion, they mean no acceleration. The velocity time graph tells the same story. With the downward positive, it starts at zero with a gradient almost g. As drag grows, acceleration and gradient decrease, and the trace approaches the first terminal plateau. Since acceleration changes, the constant acceleration Suvat equations cannot be applied across the whole fall. Now, when the parachute opens, the weight is unchanged and the velocity cannot change instantly, but the canopy produces much more drag at the same speed. Drag therefore becomes greater than weight, and the resultant force and an acceleration points upwards while velocity still points downwards, so the skydiver slows down. As speed falls, drag falls too. The upward resultant shrinks until drag again equals the weight, acceleration returns to zero, and the skydiver continues downwards at a second much lower terminal speed. On the graph, parachute opening is not a vertical drop. Velocity remains continuous, but the gradient changes sharply from zero to negative. The trace then curves towards the lower horizontal line above the time axis. That plateau means constant non-zero velocity. It doesn't mean it's at rest. The parachute has not reduced the skydiver's weight, it's just produced enough drag to balance weight at a lower speed. What determines terminal speed? For this skydiver, upthrust is negligible, so drag equals weight at a terminal speed. A larger area or a more drag-producing shape reaches that balance at a lower speed. For otherwise identical objects falling through the same air, the heavier one needs more drag to balance its weight, so its terminal speed is generally higher. Not every heavier object falls faster, however. Now, switching from skydivers to cars. On a level road, a vehicle reaches a maximum speed when its available driving force equals the total resistive force. The resultant and acceleration are zero, but the vehicle will keep moving. All else equal, more driving force or less resistance raises the maximum speed. For an exam level explanation, keep the causal chain in order. As the speed rises, drag rises, so the downward resultant force and acceleration decrease. When drag equals weight, the resultant force and the acceleration are zero, so velocity is constant. For a parachute, add that drag exceeds the unchanged weight before a lower balance is reached. Terminal speed is not where the forces disappear, it's where they balance. In the next lesson, we will use forces acting over a time to understand momentum and impulse.